Hi, everybody. My name is Ethan, and it is week 8 of Drexel AI summer term. It is August 10th, 2021. Now we are planning to finish this project within the next 3 weeks. And in order to do that, we have to work on a couple of things. The one thing that is on the front of all of our minds is going to be the paper. I'm actually going to spend some time today after this meeting, maybe around 5 or so, reading it and then leaving changes in blue. So I'm going to force myself to do that because I haven't read through it yet. And I know that you guys have been adding to it, which I really appreciate. And we have plenty of sources that we can refer to. So that makes my job a little easier as the first author who wants to just compile it so it all flows in the right way. Second of all is the algorithm and actually compiling the results. So this works, as in it runs, and we're able to get results from the genetic algorithm function. The one thing that we don't have right now is we don't have a benchmark. So what you might see here is that we are basically we're grabbing the weights. We're finding the best weights by minimizing the reconstruction loss of a dictionary learned on a data set. And we need to compare the predictions using this loss. Sorry, we need to compare the predictions of an LSTM using these weights against some sort of LSTM. And what I thought we could do is basically run this genetic algorithms for so many epochs and then train an LSTM for a number of epochs that kind of matches that number and see whether ours performs better given the weights that we have found from the algorithm. So I have it set it going at 100 children at most for 20 epochs. I think are the epochs even used here in the genetic algorithm? I don't think they are. No, they're not. But does that make sense? We at this current moment, we don't have a benchmark to compare the weights we find. We don't have a way to identify whether the weights we find from the genetic algorithm, whether they're better than our current, than like the gold standard. And the gold standard that we're comparing it to is just the LSTM model that we have here. What we might even want to do is we might want to save the weights that the first generation uses for one of the children of a given generation. So for the first generation, save the weights of the best child of generation 1 and compare it to how the weights perform of generation 10. That might be the best way to go about doing it. So what I mean is, if we think about like a timeline, right? You can kind of think of this as like a timeline. We're gonna compare. This is a timeline of generations, so G. So we're gonna compare the weights we get from generation 1 to the weights we get from generation 10. The idea is that when we train the LSTM model, when we use the LSTM model, the LSTM model should perform better on generation 10 compared to generation 1, because as we go from generation 1 to generation 10, we're selecting weights that minimize the reconstruction loss of our predictions with respect to our training data, or our feature set, right? So that's the idea. And I think that's an easy way to go about doing it. And an easy way to do that is just to, does anybody have any questions with just that idea? Just using the original, basically saving the weights from generation 1 and then comparing against generation 10. So we could just do like original weights. and then score index weights. And then it's as easy as saying if generation equals 0, we're going to set original weights equal to weights, like that. And then we can just return original weights and then these new weights after 10 generations. Return that. And then we need to compare the LSTM model. We need to run the LSTM model using the original weights and then using the new weights and seeing whether one performs better than the other. And if it does, that means that by selecting weights in a genetic algorithm manner, by minimizing the reconstruction loss, that is a effective way of improving an LSTM model or improving some sort of predictive model. And that would be, I think that'd be a good evidence of that the method works. I'm going to change things. So new weights, we have to say that weights goes right there, goes right there, goes right there, I think. Yeah, that makes sense. Okay. And then all we got to do is in the main function, we're going to go to the predict forecast. Yeah. We're going to run two models. The first model is going to be trained. So predict forecast, does that do testing as well? Yeah, it does prediction. We're going to run it on the entire data set. Actually, I don't know if that's a good idea. Should we do, I mean, I kind of want to have I kind of want to do like, okay, here's what we're going to do. I want to run it off of a new data set. So we kind of do the whole testing thing, right? So what we're going to do is we're going to do or let's say get results, and we're going to give it the original weights, the new weights, and then X and Y, and then comparison or results. The idea of the get results function is it's going to do two training and testing, but it's not going to do any sparse learning. Def, and we're going to say get results, original weights, new weights. We're going to say whether the original weights perform better than the random weights. The original weight, did I spell original right? Original. Whether the original weights from generation 1 are better or worse than the new weights from generation 10. And for that, we're going to want to do some sort of, let's do X partition. So we're going to partition it up such that we have data that we're using for the learning of the weights, and then data that we use for the testing of the weights. So it's kind of backwards, right? We're doing training and testing on two levels. We're doing training to find the weights, and then in finding the weights, we split up again to training and testing right here. So that might just be the best way to do it. So we have X and Y. We're going to need to do another split here. So this could be like X train, Y train, X test, Y test, and X test. And when we use predict forecast, when we set the weights, I don't think we want it to fit, do we? No, we don't. So maybe we don't want to run this function. Yeah, we don't want it to run this function. So fit is equal to false, or fit is equal to true. Okay. So in this case, we're not going to fit, right? We are going to adjust the weights because we're getting the weights and we just want to predict. And that's going to be how we gain the scoring. So that's going to get the score fit is equal to. We're going to have X train, X test. So do we need to give it training and testing? Here, predict forecast. Because train and that's only really used when you're testing the you only use the training data when you're doing the fitting, right? You don't need this stuff until later. Just kind of backwards actually, because you need the shape of it. Huh. Here. I don't think this predict forecast function works well for what we want it to do. So instead, I think what we need to do is just do model build, model set weights, and then model predict. So we're going to do model set weights, and then we're going to do. You need to reshape the data as well. Scalar fit, transform, reshape. So right here is going to be testing. That. And I'm going to say test, 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 test. We're going to make a new scalar because that's how we trained our model. So it has to do the same thing here now. And test, test, set weights, original weights. Train it on that. And then we're going to do the same thing for this right here. We're going to do it for the second one. So this is to evaluate the original weights. And this is to and then we don't want to use predict forecast. We simply want to use predict like this. Right? Yeah. Original, new. And then we want to see which one is better than that one. So we're going to need a metric. So let's do RSME and R squared. So I think it's under like SciPy. Is it SciPy RMSE? Okay, sklearn metrics, mean squared error. I'll take that. think it's also sklearn 2. Yeah, R2 score. We're gonna use these two metrics. One's gonna be we're gonna try to minimize one and maximize the other. And we're gonna say, okay, how does, we're gonna return tuples. First one's gonna be the original one. Actually, the dictionary. Let's do one is gonna be, this is easier actually, dictionary of a couple things. It's gonna be this is just a way to return results. It's going to be original weights. I think I'm spelling original wrong. Yeah, no one corrected me. Very upset. Well, you're spelling it like a goofball. There we go. And then we're going to return, this is going to be RMSE, and then R2. Same thing here. We're going to do like RSMC. What do I import? Mean squared error. Oh, that's mean squared error, not root mean squared error. Let's learn. Let's see. Okay, you have to do square root from math. That's fine. It's no built-in for. No built-in for, or there's no function for RMSE in scikit-learn. Squared error. And we're comparing the predicted for the original and then the test. And then we're doing the same thing for this one, but we're using the new weight, so it's the new predicted. And then we're going to do the R2 score for original and test. And then the R2 score for predicted and test. Okay, so now this function will take in the original weights and the new weights that's found by the genetic algorithm. And
I have a question for the new weights for the R2. Why are we using the original, not the new YPRED?
Thanks.
Yeah, no
there we go. Yeah. Okay. So now this function will take in the original weights and the new weights, an X test and a Y test, which will be part of the training set of this whole, whatever, this machine learning algorithm. And then our output is going to be these metrics that are going to be important for comparing whether the original did better than the new or the new did better than the original. So in our case, we want the second one to do better than the first one, because otherwise we spend all this time doing nothing. So I think that works out well. We'll get the results, and then the one thing that we're missing right now is we need to basically give the genetic algorithm X train and X test, and we need to give this one, X train, Y train, and then X test and Y test. And then in the genetic algorithm, this is going to be further broken down into a train and test set itself. So I used, I get the train and test set in the genetic algorithm by doing, where is it? I do 10-fold cross validation, but I don't know if I want to do that for this. That's like the best way to go about doing it, but that means I have to wrap this entire thing in. Actually, go big or go home, I guess, right? Okay, so let's do that. So k-fold, we'll do 10-fold just to make it easier on us. So the data we don't need to get every time. Segments we don't need to get every time. What we need to do every time is this. So 10-fold cross validation for people who don't know. If you have like a data set that is like 1,000 long, and you do like 10-fold cross validation, you're saying I'm going to generate 10 different versions of this data set, and I'm going to segment it into training and test sets where for each fold, 1/10 of it is for testing. So like 1/10, so there's 100 here, is used for testing. And then the 90, the other 90% is used for training. So like the 900 would be used for training. And then in the second fold, this partition would just move right here. So this wouldn't be used for training. 100 here would be used for, testing. And then the 900 that's left over would be used for training. And after all 10 finishes, you can just average the metrics from, you can average like the accuracy or the RMSE from all 10 folds. So that's exactly what we're doing right here. It's a very very good way of testing a machine learning method, in my opinion. So we're going to just do this. So this adds another level of complexity to all of this, because we have to run it on all of the data multiple times, which is, it's wonderful, right? Results equals a list. I think you can do equals. You can do list of dictionaries. I'm just going to make sure before I implement it. And you're just going to do print results. Actually, there's this library called Pretty Print, and it's used to make dictionaries display better. So I'm going to use that each time. So it's just p print right here, and you're going to say results. Results, and then results 10, like that. And then we can basically parse this results list for all of the result dictionaries inside of it. And then after this, we're going to be like done. Just return like 1 and exit that as a 0. So it finishes correctly. And I think that's it. Right, we got to say 10 generation, 10 folds. Say and folds equals 10. We're going to say I fold equals 0. We're going to say generation. Not doing generation, running fold like I fold. Fold. A trick I recently learned is in regard to like printf. I think if you use a carriage return, oh, no, it doesn't do it.
You'll have to put curly brackets around the are you talking about f strings?
Yeah, so I'm trying to do the carriage return thing. Do you know how to use a carriage return in Python?
So
carriage return makes it so that you're writing over the same line, but you basically
that's B, I guess. That's
Is it,
B.
it's B?
Yeah, for backspace. Because
I don't think so. I'll Google it real quick. Here we go. In R, what it does is it when you do carriage return, it'll print it, but then the cursor will go back right here, and then you can continue to write over that line. So instead of getting something that looks like something that looks like this, it'll just update the line without like adding more text. It's a really neat way to just make things look better instead of having a long list of text, but it's fine. So we now should have a way to get all of the results, and I'm going to save these results to a file because I always forget to do that. So I'm going to use pickle because I never do this. I never do the whole saving thing. It screws me over whenever I want to use results in the future. Okay, so results, we don't need this. I'm going to write to a file and then dump it in there. And we're going to load pickle there. And then the file name that we're going to write it to is going to be wherever our working environment is. So it's going to be here. I wonder if you can get like os dot I want to make it so that it's useful in your so you guys can run it. So from os imports current working directory. There we go. Working directory. There we go. Oh, we're going to use this then. I'm going to open, and then I think the way to do it is to get current working directory from OS right here. And then we need to also use, also use a function that merges oh yeah, OS path join right here. So we're going to do something like this. So everyone on Windows will be able to do the same thing. So right here, and then we're going to call it results dot pi dot pickle. I don't know. File extensions really don't matter. Okay. So yeah, let's review what happens in the main function now, because it just got a lot bigger, and I might add this to a function itself. So what we're doing, actually, no, it's fine in the main function actually, because it's running the entire thing. What we're doing is we're setting a temporary directory. Now I have this set for me, but this probably won't be what you guys would use. You'd probably use something else. So I actually might want to do like this, actually. There we go. Makes it easier. So now you guys don't have to change it. So we're setting the current working directory to here, and then we're loading data in the current working directory. So it's going to dump all of the data into, actually, sorry. Yes, okay. I have this set for one reason, and the one reason is because I loaded this. I ran this command without giving it tempter, and then I moved the data from tempter to this directory. That's what happened. And now that I'm running it a second time, I can set it myself. So only set and use tempter this way when data must be downloaded using data into a temp directory and moved to this predefined or this defined location. Launch, for example, you'd run load data without the tempter as an argument. You'd move data from tempter to this location, and then every other time when you use tempter, every time when you're going to use load data, you're just going to give it this file on this location on your computer. The next thing is we get the segments, and we control how many patients we look at and how many samples we want to look at. So right now we're getting 50 samples in X and in Y. So the dimensions of not defined. The dimensions of this will not be defined actually because I just opened a random pi. The dimensions of X will be 50 by however many features we have. I think we have 64,000 we're using to generate the sparse representation, which might be too many, I don't know. And then Y will just be 50 by however many we're trying to predict, which will be 128. And then this part is to basically run the genetic algorithm and then test the weights 10 times. And in each of these 10 times, we're using a different portion of the overall data set we have. So we're just splitting the X into 10 folds, and then we're evaluating how well we perform on each fold. And then we're appending the results to a list, and the results underscore as a dictionary, we're appending it to a list, and then we're saving it to a results.pickle file. And then I can load that in and then do the analysis later. And that should be it, actually, now that we're all done with it. What it'll look like when people run it on their computer is a long list of this where you have so many children. I still have to play with the numbers because I think 100 children is too many. We might want to do like 10 children. The thing that stinks with this is that the number of children you pick actually influences, so we don't need epochs here. We need children and generation number. The number of, I'm just gonna get rid of this here. The number of children you pick matters, and the number of generations you pick matters too, because those are used to determine the dimensionality of, it's used to determine the dimensionality of the dictionary, which is something I don't exactly like. And if the dimensionality of the dictionary is wrong, then it breaks everything. And I don't like that happens. So if I ran it right now, it would break because I haven't figured out what dimensions are needed in order to make it so that we can, learn the dictionary and then use that dictionary on the test set. And I would like to figure that out so it's usable by other people. Because right now I have the batch size at 200. Filters 200. Pages per images, and the dictionary filter size is 32. So that's already set. And I think that when we, I've gone back and forth with Osamu about, what we need to do to make sure that the dimensions line up, and I haven't figured out the best way. I'll also work on that today. Actually, let's do that right now. I'm going to do that right now. on the algorithm. And I guess as we do this, we'll find bugs. Better to find them now.
I think it's exit to.
It's fine. Basically, I just want to stop so I can use it. I don't know if exit would actually exit the console. You know what I mean? Also, we need to change this to, actually, that's fine. We should have moved it down farther. X is not defined. Sure. Sure, X isn't defined. Data is not defined. Did I do something wrong? Oh, it's because I'm in the, that's funny. Okay. That's fine. Because I was running it in the main, I'm not running it in the main function, I'm running it in the main function. Okay, and now we can just grab our testing sets and training sets. And I think that we run it here. We're going to get an error because before, the number of samples we had in X was 64,000. And now of X, right? X used to be 64,000 samples. Oh, I'm sorry. X used to be 50 samples. Oh, it's working. I think it's fine. X used to be 50 samples and now X test, or sorry, X train, X. So we're splitting up the 50 samples in get segments. We're splitting it up into 90 and 10. So now X train is 54, sorry, is 45 samples. So 45 samples goes to training, and then 5 samples goes to testing. But the dimensionality of each sample is still 64,000 long. So I don't know if I know that the sparse coding will break if this number it changes from what it's currently at. I don't know if the number of samples influences it. It might. But if this works out well, then I will not complain. Sorry, I know I've been jumping around a lot, but I really just wanted to get that done so that I can run it and, read this paper while it's running tonight. The one right here. And I'll leave comments. Do we have any questions about what I did today, or, the progress? No? Okay. Really hope this doesn't fail. It's going to take a long time for 2 reasons. Number one is if we have 10 folds, it's going to have to learn the sparse representation 10 times, right? Because it's independent of each training set. Each training set is different. There's some overlaps in between them, but it's the whole 10-fold cross-validation thing. And then because we have to basically train and test a model pretty often. So that can be added to the conclusion where we talk about the limitations, right? This requires a lot of testing, a lot of training, because if you want to if you want to train it, you have to get a sparse representation of the data set, get a sparse representation of the entire data set. And then if you want to, validate it, and make sure that it's doing well, you want to do a k-fold cross validation. In our case, it's 10-fold cross validation. And then for each generation, you have so many children that you're going to, for each generation, you have so many children you're going to predict and train a model for. So if we are doing 10 generations, we have 25 children in each generation, that's 250 times we have to train and test the model. The good thing is that if this works well, then that is it's a big upfront cost, but then you might have a more accurate model you could deploy. So there isn't any loss in the model when it's deployed, because you're using the same model architecture, but the idea is that the weights are better, or they should be better, because we are prioritizing weights that minimize the reconstruction loss of a predicted signal. That's what you got to do. That's what you got to say. We are prioritizing weights that minimize the reconstruction loss of a predicted signal using a dictionary from the feature set. Yeah, cool. So I will, I guess, not let this run because I have to run it. I have to run it again, but I'm just happy that this didn't break. I might run it for one fold first, make sure it runs through one fold, and then run it for everything else. We are only looking at 50 samples right now, and I'm not sure if we want to do more. For instance, we could do like 500 samples. I don't know what's a good number, because of the fact that we're getting so many, because of the fact that there's so many dimensions in each sample, right? You have in a sample, in one sample, you have 64,000 points, and that might be too many actually. But I think we're fine, because our data is 1,000 hertz. So that's only 6.4 seconds. So I don't think that's unreasonable. No, that's 64 seconds. So it's about a minute. So training for a minute and then being able to predict the next tenth of a second, tenth of a minute, tenth of a second. Yeah, that's what it is. Yeah, training for a minute and using that minute to predict the next tenth of a second. And then, we could always extend this to see, okay, what if we wanted to predict the next 256 points? So we're predicting 2/10 of a second, and then we could see how far that take us. And that could be a next work for this. Like for this term, we might focus on just getting the algorithm established, A, and B, showing that it works on this 64,000 and 128 split, because in segments you can actually see that's where we set up the dimensionality. So it's really easy to change the dimensionality of the data right here, because you can change it. It's like the feature data points and then the target data points. They're just features here, but changing these values will affect how the sparse model works, because I think that when you set a dictionary size of 32, it has to go evenly into both this number and then this number in our case. I don't do much over the weekend, so what I'm probably gonna do is just run this, not starting the weekend, starting like tonight, and then if there's any issues, I'll fix them and I'll figure it out. Because I've had it run like all the way through, or seemingly all the way through, for for all of X and all of Y. So all we did is we added a way to collate the scores, get the results, append them to a list, and then also the K-fold validation. So there might be in some of the things that we added, I overlooked some details that'll cause it to fail. Good testing practice would be to, do unit tests on all these things to make sure that they individually work. But that requires a lot of time, which I do not have. Cool. All right. Yeah, do we have any questions? I think that's it for me. No questions? All right. Thank you for joining in. I'll let you go a little early. If there's nothing else, I'll see you next week at week 9. Hopefully, the paper will be cleaned up, and I'll leave comments in blue for all those who want to look at it. One other thing I want to add is that the Theta Tau fraternity is hosting a volleyball tournament in the fall for a fundraiser. I am attending to represent Drexel AI, in addition to Drexel Biomedical Undergraduate Association. And I'll come back with details hopefully next week about what that'll look like, when it is, who's participating. I know that they wanted to invite a lot of clubs. So maybe, you guys could be involved with that as well, like showing up, playing volleyball. I mean, I'm not all too good at playing volleyball. I'm actually pretty bad at the whole land sport thing, but I can play a little bit.
What about the RC car thing? Is there any updates on that?
Not with that. We're still waiting. I probably should reach out to them about like getting a Zoom together, but if they're as serious as they seem that they were, then I'm sure that they'll get back to me in a couple weeks about that. And then Alicia, you're CC'd on the email thread, right?
Yeah, I think so. Yeah.
So that'll happen, and that'll be interesting because I know squat about computer vision. But cool. All right. Have a good week, guys.
See ya.
See ya.